Hello lovelies, in this video I'm going to take you through my WJEC double science physics paper 2, the predicted paper that I wrote for 2023. Now this is a very maths heavy paper, but do not let that scare you because this is a brilliant easy way for you to pick up marks and it shouldn't be scary and intimidating at all. I'm going to structure things, I'm going to walk you through things so you can see how you can pick up loads of marks in the real exam. I'm going to do some colour coding for you. So blue is going to be exam skills. This is a maths paper. So we're going to have lots of maths in physics skills. So command words, how to structure your maths skills here. In purple, we're going to have background knowledge. We're going to have the science bit, anything you should be able to recall from class. And then in pink, we're going to have the actual answer that I would write if I was sitting this as an exam. There are two factors that affect how long a car takes to stop. Together, these give us the stopping distance of the car. State these two factors, and this is for 2 marks. Now, because we need to state two things for 2 marks, you are not going to write a lot here. We're looking for simple answers, 1, 2, 3 word max, definitely not full sentences. So there are 2 parts that make this up. We are looking for the thinking part, the human part, so the reaction time, and then the car part, the braking distance. Now we have a maths question, which I know lots of you don't like, but I'm going to show you this method is going to give you so many easy marks that you will smile when you see a question like this in the exam. As part of your membership, you get access to the practice, the workshop that I did on how to do maths in physics, so please go and watch that. Step number 1, highlight the numbers in the question with your highlighter pen. The fact that a car travelled home to school, from home to school, isn't actually relevant to our answer. Then once you've highlighted the numbers, what I want you to do is to go through, pull all the numbers out and then pop them over here in a section where we can clearly see what is going on. So we have force, which is 55.5 kilonewtons, important there. We have distance, and that is 3 metres. And we have the mass, which is 1,500 kilometres. Now we can see we have kilonewtons. These are non-standard units, and before we even think about an equation, I want you to convert these units. If you leave converting it until you're in the middle of an equation, you're more likely to forget. So let's do it now. So to go from kilonewtons into newtons, we need to times by thousands. So there's 55,500 newtons. Then we can start to think about an equation. We are looking for acceleration in this, and we have force and we have mass. So the equation that I'm going to use, and I'm writing this out in full, is force equals mass times acceleration. Then I'm going to substitute in the numbers, writing them directly below the bit that I'm talking about, and then writing acceleration out in full. No shortening going on here. So you'll see that I've substituted before I've rearranged. This is coming from the examples. This is what they've suggested that you do to get the marks. Then we can rearrange, so 55,500 divided by 1,500 equals acceleration. Again, really clearly laying it out. Gives us 37 meters per second as acceleration. Now, we've worked out the acceleration here, but we need to use a little bit of logic. The car was travelling and it came to a complete stop. So the car is slowing down. So this isn't actually acceleration we've worked out. This is deceleration, which is going to give us a negative number. Now, I've put in the mark scheme for this that you can have the marks whether you give a positive or a negative number, because I think this logic step is quite hard. But it is something you should pay attention to in the exam. Thus, and whenever we see thus in a question, it means that we need to follow on from the information before. Calculate the velocity of the car just before the brakes were applied. If no answer, blah, 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 right, but we have found the answer, so we can ignore that. And it says give your answer to 1 decimal place. So calculate the velocity just before the brakes were applied. This is going to give us the initial velocity. And then we need to go back to the question. Always, if there's a bit of information you think is missing, and go back to the question. The car came to a complete stop, a full stop, which means the final velocity is 0. Whenever you see initial velocity and final velocity, that should be kind of like triggering in your head that we're going to be using your what are called SUVAT equations. So the equation we're going to use for this, and again, I'm going to write it out in full just so the examiners don't misunderstood my U's, my V's for anything else. Final velocity squared minus initial velocity squared equals 2 times acceleration times distance. So I know this is quite a lot to write out, but you're getting 5 marks for this question and you still haven't written a huge amount of words. So final velocity is 0, so 0 squared minus initial velocity squared equals 2 times acceleration, which we worked out as minus 37, times 3, which is our distance from the initial part of the question here. So doing the maths there, we've substituted things in. We have minus initial velocity squared is equal to minus 222. Because that minus is on both sides, we can times that by minus 1, get rid of that negative, and all we need to do is to square root that 222. This gives us the answer of 14.9 meters per second. Now, we need to look at this bit here where it says give your answer to 1 decimal place. The calculator value that is going to come up with when you square root 222 is 14.899664443. This is not to 1 decimal place, so we need to do it to 1 decimal place. Whenever you see that, it's a clue from the examiners that there is going to be a mark on the mark scheme specifically allocated to rounding to a decimal place or a significant figure. So please don't ignore that. I know it's easy to because it's right at the end. When we're doing decimal places, we need to look at where we want to put our decimal place and see if the number after it is above or below 5. And if this one is above 5, so we need to round that and make that one bigger, giving us 14.9. If you wrote 14.89 or something else and just didn't round it to significant figures, you would only lose 1 mark. The journey that the car took from home to school is described below. Sketch a distance time graph for this journey. Whenever we see sketch as the command word, we need to have the axis, we need to have labels. It is not points, it is not joining the dots. So I'm going to have my axis drawn. Well, you should do it with a ruler, definitely. We're going to need to label the axis, and for a distance time graph, you need to have time going along the bottom and you need to have distance going up the side. And of course, we're adding in our units. Now we've been units in the question, so meters would be most appropriate. Here is home. We leave home, which means we are travelling, we are doing some distance over time at 7:45. So we keep going for 8 minutes. So I'm drawing a line. This is just a sketch graph, remember. Stop at traffic lights 4 minutes. So stop, we're stationary. Time is increasing, but distance is not increasing. Get caught in lots of slow traffic, so the gradient here needs to be shallower than here. See a cat running across the road, that's the bit we just draw. So we slammed on our brakes and we stopped for a bit, and then we continue and we get to school. So when we're sketching this, take this slowly. Make sure each part of the line matches up with the description in the question. Describe how different factors can affect the stopping distance when a driver is braking. So this is a 6-mark question. We can see 6 marks there. We should immediately be thinking this is our level response answer. So your answer needs to be logical, it needs to be coherent. We know from the first part of the question that stopping distance is made up of 2 things. So reaction time, the thinking, the human part, and braking distance, the part that's relevant to the car. So this is going to tell us how we're going to structure our answer. We're going to have 2 paragraphs here. There are a number of things that could affect reaction time. The reactions could be slowed down, thus increasing reaction time. if the driver is tired or distracted, or under the influence of alcohol. So I've listed 3 different things there. All of these would increase the stopping distance of the car. So I've listed 3 things and I've clearly stated what it would do to the stopping distance and that it's linked to reaction time. The braking distance of the car can be affected by the mass of the car. So I've stated a factor, now I'm going to use physics to explain why. Using force equals mass times acceleration, we can see that a higher mass would need longer time to decelerate, assuming the same force is applied. The conditions on the road, e.g. icy roads or worn tyres, would reduce friction and increase the stopping distance. So you can see that I've stated what it would be instead of just saying, oh, the mass is going to affect stopping distance. How is that going to affect stopping distance? I've been all fancy and I've used equations in there to show that. I didn't mean to have that out. And I've linked everything together. Drugs is generally a bad answer for this because some drugs will slow down thinking times and some will increase thinking times. For example, caffeine is a drug, but it will actually make your reaction time faster. Also saying illegal drugs, well, that is also a bad thing because some illegal drugs will speed up your reaction times and some legal drugs, for example sleeping tablets, will slow down your reaction times. Drugs I would generally say avoid unless you can't think of anything else because it is just, there's too much detail and nuance in there to be a clear answer. Things like alcohol, tiredness and distractingness are going to increase the time the driver takes to react, thus increasing the thinking distance of the car. Here we can see our mark scheme, and you can see for the maths questions the same sort of things come up over and over again. Equation, substitution, rearrangement, units is an important one. Please show new units. Get this on a flashcard if you're not 100% sure. We can see our rough sketch for this. You can see that there are no numbers plotted on here, so it is just a sketch graph. And for our level response marking, you could see that I've put here that I've put bullet points here, but you can see actually just bullet pointing things, distraction, tiredness, that's kind of like not very logically linked. Whereas if you want to get 5 to 6 marks, fully coherent and logically linked. A student carried out an experiment to find the spring constant of a spring. The table shows the data collected. So this is a practical hopefully you've done in class. You might have called it something like the Hooke's Law practical or extension of a spring. Or you might have used an elastic band where you were just hanging different masses off and measuring how long the spring was. The table here is what you would have measured in class, and it's draw a second table to determine the values needed to plot a graph to find the spring constant. In the first table, we can see the measured values, so the masses that were added and the length of the spring. But to find the spring constant, we need to have some calculated values, and it's given us a clue where it says, use the value for 10 newtons per kilogram for gravity. So here is our table. Now I'm doing a slightly larger table than I've written in the mark scheme, just because I want to show you exactly how things relate to each other. So in my first column, I'm going to have mass. This is going to be the same as it is in the question. The next column is going to be the weight, which is measured in newtons, then the length of the spring, and then the extension. So the 2 things we're going to be calculating are the weight and the extension. Now, we need to use weight equals mass times gravity, and we have the value for gravity. You will notice that the length of the string is in standard units, meters. However, the masses that have been added are in grams. These are non-standard units because our standard units for mass is kilograms, not grams. So the first thing we need to do is to take all of those masses and convert them into kilograms, and then we need to convert it into weight, into newtons. So there is quite a lot of maths here. I'm going to write all of these out fully, but hopefully you'll see that there's a pattern and it won't actually take very long in the exam for you to do it. So the first thing is converting grams into kilograms. So if we have 100 grams, convert that into kilograms, we need to divide that by 1000, which will give us 0.1 kilograms. Using weight equals mass times gravity, we are looking for the weight. The mass is 0.1 kilograms times 10, which is gravity, and that will give us 1 as the weight. I'm sure you can see the pattern starting to emerge here. For the next one, we have 200 grams divided by 1000 gives us 0.2 kilograms. Weight equals mass times gravity, so that is 0.2 times 10, which gives us 2 newtons. For the next one, we have 300 divided by 1000, which gives us 0.3 kilograms. Weight equals mass times gravity, so 0.3 times 10 gives us 3 newtons for the weight. And then the last one, you don't have to write all these out in the exam. 400 divided by 1000 gives us 0.4 kilograms. Weight equals mass times gravity gives us 0.4 times 10 will give us 4 newtons. So there we have worked out the weight for everything. Now we need to work out the extension. Now when there is 0 masses added on, there has been 0 extension. So what we need to do is to use this number here as our 0. So to work out the extension is the measured length of the string minus the 0 value. So we need to take all of these values and minus 0.170 from them. So we have 0.235 minus 0.170 will give us 0.065. 0.300 minus 0.170 will give us 0.130. 0.365 minus 0.170 will give us 0.195. 0.430 minus 0.170 will give us 0.290. Lots of maths there, but in the exam you wouldn't need to write down all of your working. There are 2 ways to determine the spring constant of a spring. From the data collected, give both methods. So depending on the graph that you draw, it will either be the gradient or it will be the inverse of the gradient that is drawn. Or the easier way, the much easier way, which I suggest you do, is using the equation, which is force equals the spring constant times extension. Draw a graph that will allow you to determine the spring constant. Now, you could have done this a couple of different ways in class, and I've allowed you either way based on the mark scheme. I'm going to show you one way and then I'm going to explain the other way to you as well. Please, when you're doing this, use a ruler. So here are my axes. I am going to put extension along the bottom and I've labelled it and I've given my units in meters, and then I'm going to put weight newtons up the side, and I'll show you why in a second. If you've drawn yours the other way around, that is perfectly normal, that is absolutely fine. I'll explain the details in a little bit. So I'm just dividing up my graph here with the axes, labelling the units on there. And I'm just going to pop in the table from the answers so that we can see what I am drawing where. So we've got the numbers quite and easy to hand. So 0 is 0, and then when we have 1 Newton, we are going to have 0.065 as the extension. Whenever you're drawing graphs in science, doesn't matter whether it's physics, chemistry or biology, please use a cross. If you draw a massive dot like this, it's really hard for you to see, or the examiners to see, which point you're actually referring to, where a cross is a lot more detailed. And please use a really sharp pencil. I'm drawing with a stylus on an iPad, so it might not be 100% clear, but it needs to be clear to the examiners which point you're referring to. So at 2 newtons, we need to be at 1.3, so just there. And then at 3 newtons, we need to be just before 2, so 1.95. And then the last one at 4 newtons, we need to be at 2.6, so we go to 2.5 and just go past 2.5, work our way up and pop in across. And then we need to please use our ruler to draw a line of best fit. And remember, this needs to go through the origin, through 0, 0, because there is no extension if there is no weight added. And there we have a very nice looking line of best fit. And the next part says, determine the spring constant for this in newtons per metre. And that is why I've drawn the graph this way around. So I'm going to show you the two different methods. The method that I recommend that you use unless it specifies to use the other method in the exam. If it specifies which method to use, you don't have a choice. If you get given a choice, this is the easier method to use because we're just doing maths. So force equals spring constant times extension, and then you can pick any set of data from the table. So I've gone for the 4 newtons being added, so 4 equals spring constant times extension, which is 0.26. So I've written down my equation, I've substituted my values in, and then I've rearranged. So 4 divided by 0.26 gives us a spring constant, which will give us a value of 15.4 newtons per metre. Now in the exam, if you're slightly stuck for remembering units for things like spring constant, there is a trick we can do. If you replace in the equation force with the units of force, spring constant is the one we're unsure about the units, and then extension with the units for extension, we rearrange it and we get newtons per metre as the units for spring constant. I've drawn the graph this way around in here because it's easier to find the gradient because it's already the right way around. So here we can find the gradient of the line, and all you need to do for that is the change in up, so the change in this bit here, divided by the change in across this bit here. What you would do is basically draw the biggest triangle possible and would actually just involve using exactly the same numbers because it would be here and it would be here. If you've drawn your graph the other way around, because the mass was the independent variable, so you put the weight on the bottom here and then the distance up the side here, what you would need to be looking for is the inverse of the gradient, because your mass will be the other way up. You would have done 0.26 divided by 4, and then you just take 1 and then divide that by the answer. As long as you explain it clearly in the exam, unless they've specified, you should get marks for doing it either way around. State how you could determine the work done when stretching this spring. So this is a state, not a calculation, because that is coming later. And the work done, the units for work done are joules. This should be ringing bells. Whenever you see work done, you need to be thinking about energy. So we are stretching a spring. This is elastic energy, elastic potential energy. So what equation can we find out? What equation can we find from our equation sheet that has elastic potential energy in it and also has the spring constant in it? That is, elastic potential energy equals 0.5 times the spring constant times extension squared. Thus, which means we need to use the data from previous parts of the question, calculate the work done, or the elastic potential energy, to stretch the string 26 centimetres from the original length. So that is the extension there. So we can substitute in numbers. Elastic potential energy equals 0.5 times 15.4. That is the spring constant that we got from the previous equation. And then 26 centimetres is non-standard units. We need to convert those to metres. 26 divided by 100 gives us 0.26, so it's 0.26 squared, which is going to give us a final answer, 0.52 joules. That was a rather massive question, but you can see the mark scheme isn't too complicated for this because it's just a lot of things you need to get right. Again, we can have whether you're using the inverse of the gradient or the gradient depending on which graph you've actually drawn. For the last part, again, nothing too unusual here because it's just physics. Here we have a setup for a practical. Now, when you've done this in class, You may not have done it exactly like this, but the equipment is set up in the diagram to investigate how varying a force on an object accepts the acceleration. Now, when I've seen force and acceleration in the same sentence, the thing that's immediately sprung to mind is force equals mass times acceleration, so I've just written that down. And we have gravity. They've given us a value of gravity as 10 newtons per kilogram, so that brings to mind weight equals mass times gravity, another equation we can use in this. Now, this is a practical you should have done something similar to in class. So lots of different things you could have changed, or your teacher could have changed about this. I've drawn a picture of a block here. It might be a car, or it might be a trolley that you've used in class. I've done this on a flat surface, but you might have done it on a slope. You might have used light gates instead of ruler markings or something like this. So it was using a computer to automatically measure the time that it moved in the distance. All of these changes to this practical, they all work on the same principle, but you can expect to see the practical in a new context. So even if this isn't exactly the same as the one you've done in class, there's no reason you can't answer these questions. To get the results for this experiment, several measurements need to be taken. Describe what these measurements were and give their units. Now, this is for 4 marks. And this is where we can start to try and guess what the examiners are looking for, try and guess what the mark scheme would be saying. So we need to give the measurements and the units. Now, units are really important in physics. You need to learn them. Please get them on a flashcard if you don't have them already. You will not be given these on the equation sheet. So we can make a logical guess that for 4 marks, you need to give the measurement you're taking and the unit for the second mark, third mark, another measurement, fourth mark, the unit that you will be using. And there are loads and loads of things you could write down for this. One of the clues left for you in the exam question is distance. Well, that is a measurement that we need to take. So the first thing I'm going to write down for my answer is distance. And I'm going to measure that in either millimetres or centimetres. If you put down metres, that's not a very realistic number here, because there's no way you could think the distance between here and here is more than 1 metre. So metres would not be a very realistic answer here. Millimetres or centimetres would be the better choice. Another one we have here is a stack of masses. So mass, that's another thing we need to measure. And the unit for mass is kilograms. So another thing they want to look at, they're looking at the effect of acceleration, and for that we're going to need distance, we're going to need time. So time is something else we are going to measure. Time measured in seconds. Again, hours would be unrealistic. Acceleration is not something we are directly measuring because it is a calculated value. Another one we can pick up from the question is force here. Force is the other one we can put down, and the units for force are newtons. This has to have a capital N. If you write a lowercase n for newtons, that is not correct. That is not the correct unit for newtons. So I've just put the diagram over to the left to remind us of the setup. Describe how the force in this experiment was changed. So we need to think back to the notes I made on the previous page. The equation that sprung to mind, weight equals mass times gravity. We have our stack of masses. We can see that in the diagram. We're told in the question that gravity is 10 newtons per kilogram. That's a constant. We're not going to change it. So then we need to think about how we can link this to force. And the units for weight are newtons, which are the same as the units for force. Because the force, your weight, is just the force due to gravity that you're exerting upon the earth. So if we want to change the force, what we need to be changing is the mass of this bit here. And it is a little bit naughty of me, but I've just used the terms weight and mass interchangeably. You could either add masses to the stack or add weights to the stack. But because we've written down this equation, the examiner knows we're talking about the same thing. The mass is a control variable and needs to be kept constant. Describe how this is achieved. Now we have mass here. And if we're changing the mass, if we're going to be, so we're changing the force, How can we make sure the mass is constant? Because that is a control variable. So here we have our stack, here we have our block, and this is the pulley in between them. And you can see I've drawn 3 rectangles. So the total mass, assuming each of these is the same, is 3. Now if I remove one of these, so that I'm decreasing the mass, so that I'm decreasing the force exerted to pull it down, what I need to do is then pop it up here so that the total is still the same. So any masses that are removed from the stack need to be added to the top of the car, to be added to the top of the block to keep it constant. This is something that's quite hard that a lot of students forget or just don't understand, or may have simply done it in a practical and not really understood why they did it in a practical. So I'm going to say that the total mass of the block plus the stack is kept constant, and when masses are removed from the stack, they are added to the top of the block or the car or the trolley or whatever it is that you've got over here. At the start of the experiment, the mass of the block was 750 grams and the weight on the stack was 7 newtons. Calculate the total mass used. So whenever you see equations like this, the first thing I want you to do is highlight the numbers in the question. Now I did a massive session on this, which you get included as part of your membership if you want to go and watch basically a lot of questions like this, how to do the maths in physics. Step 2 is to actually pull all of these numbers out because we do not need all of those words in there. They're not important. So I like to write them just to the side, write little keys. So I've always got one place to go back and get all the information that I need so that I don't have to keep rereading the questions again and again and again every single time that I need to get another bit of information out. So the weight on the stack was 7 newtons, the mass of the block was 750 grams, and then from the question we know that gravity is 10 newtons per kilogram. If you feel like there's something missing, always go back to the beginning of the question, reread it, and check see if there's information hiding in there. Now at this point, what I want you to do is look for any non-standard units. So the mass on the block was 750 grams, so we need to convert this to standard units. Our standard unit for kilograms, for mass, is kilograms. We did this in the first part of the question. So to convert grams into kilograms, you need to divide by 1,000, which gives us 0.75 kilograms as our mass. Step number 4, you need to come up with an equation. So, well, not come up with an equation, find an equation from your formula sheet and then write it out in full so the examiner clearly knows what you're talking about. The one that I'm using is weight equals mass times gravity. Now, what I want you to do first of all is to substitute the numbers into the equation, and then any rearranging comes after the substitution. This is directly advice from the examiners to prevent you making mistakes, to help them give you more marks. So I'm just writing them directly underneath. So our weight is 7, gravity is 10, so I've substituted first and then we're going to rearrange. So it's 7 divided by 10 will equal the mass that is related to the stack. So what we're going to get for that is 0.7. Now it is asking for the total mass here. So what we need to do is have 0.7, the mass that is on the stack, plus 0.75, that is the mass of the block, to give us the total mass at the start, which is 1.45 kilograms. So for this, you can see it is 5 marks for this calculation. I'm just going to go through on here what the marks are for. So you're going to get your first mark for writing down the equation. The second mark is going to come for substituting the numbers in. Third mark is going to be for rearranging. You're going to get a mark for converting your units, and then the fifth mark is going to be for the answer and the units for mass. So please always write down your units. So you can see for part A, there is actually a lot of things you could have written down, but you needed linked points up to a maximum of 4 for the calculation. It is a very, very formulaic layout of this. It always is in maths in physics exams, so please learn how to do this skill properly. Describe the structure of the solar system. So this is for 3 marks. Describe is what does it look like. Now, this is a great question because there's loads of things you can write about the structure of the solar system, but there's 3 marks available here. So from a very long list of things, you only have to pick 3 things. So I'm going to say that it has 8 planets that orbit around a central sun and that moons orbit planets. Our sun is a second generation star. Explain how we know this. Again for 3 marks. The sun has heavy elements. These are made during fusion inside a star, such as during a supernova. Now, my large handwriting is a bit all out of space, so I'm going to do the next 6-mark question over on another page. Describe the path that leads to the formation of a black hole for 6 marks. This is a very short question for 6 marks. We are starting off with the birth of the star. So we are starting off with a stellar nebula. And then we're going to be going all the way through to the black hole over here. So this is the path that we are following. The one around the outside, we are ignoring the one in the middle on my diagram here. We're following the big path around the outside. So black holes form from stars that are bigger than the sun. They form from massive stars, where our sun is an average star. Stars start off as a stellar nebula, which is a cloud of dust and gas. The dust and gas is pulled together by gravity, forming a protostar. This becomes a main sequence star, and this is where it stays for the majority of a star's lifetime. Towards the end of its life, it becomes a red supergiant. It starts to expand. Then it will undergo a supernova explosion, and it will end in a black hole. You can see here the alternative is a neutron star. Now you can see here, I have not written a huge amount for my 6 marks here, but it covers all the key points. It is logical, it is ordered, it is coherent. You do not mean you need to write loads and loads of marks. So here is the answer. You can see for the first part, lots of things you could have picked from, and again, lots of things we could have picked from for our 6-mark question there, lots and lots of choice. Ouch! This is why in some videos I explain scratches.